Kirk Math. All right, here we are, the last lesson of topic 7. Can you believe it? We finally got there. And this one's all about special cases. We're going to go ahead and see how to factor special case situations of these trinomials to make it easier. So the first thing we're going to look at is what happens when we have a perfect square trinomial. We're going to know that that's a perfect square trinomial because of the following. A perfect square trinomial results when a binomial is squared. The first and last terms are perfect squares. So if I have a plus b times a plus b, that's a plus b squared. The first term, a, is going to be a perfect square, a squared. And the last term here, b, in this case, is going to be a perfect square. The inside, the middle term, is going to be twice the product of the first and last terms of the binomial. So the middle is going to be 2 times a times b. And then same if you have a subtraction perfect square trinomial as well. So I kind of wrote it out over here as well. You're going to know if a trinomial is perfect square if the first term a and the last term c are perfect squares, and that middle term is 2 times the square root of c. Okay, so we're going to take a look in this example here. X squared plus 14x equals, or plus 49. And we know that 49 is a perfect square. We know that x is a perfect square. We can prove that by writing 49 as a square of 7. And then we know that the middle term here is 2 times the square root of 49, which is 7. Okay, so because this trinomial fits the pattern, we can identify this as a perfect square trinomial. And all you have to do is find that square root of c and then write it as a, x plus 7 squared, as a perfect square trinomial. Here we have another example, but this time we have a number in front of x squared, but we still know that it's a perfect square trinomial because the first term a is a perfect square, the last term c is a perfect square, and the middle is the product, this is 2 times the square root of c. So we can see that here, that it's going to be c and a, the square root of a, when we have that term in front there. So here we can see that 9x squared, we're going to write that as a perfect square. The square root of 9x squared is 3x. 25 is a perfect square. The square root of that is 5. If I do 2 times a times c, the perfect squares of them, then I am going to get my middle term, which is negative 30x. So therefore, I have a perfect square of 3x minus 5 squared. Factoring, the factored form of a perfect square trinomial is a plus b squared when the trinomial fits the pattern a squared plus 2ab plus b squared. And it'll be a minus b squared when the trinomial fits the pattern of a squared minus 2ab plus b squared. So you're going to take the information that we just went over and you're going to go ahead and try these right here. Can you find and factor this trinomial into perfect squares? All right, so we're going to use our perfect square trinomials in a word problem here. Sasha has a tech store and needs cylindrical containers to package her voice-activated speakers. A packaging company makes 2 different cylindrical containers. Both are 3 inches high. The volume information is given for each type of container. So this is the volume of the black container. This is the volume of this blue container. Determine the radius of each cylinder. How much greater is the radius of one container than the other? So the first thing we have to do is kind of formulate our volume. So the volume for a cylinder is pi r squared 8 times h, where r is the radius and h is the height. Because the height is the same for both of these containers, they will both have 3 times pi in common. So here is the volume down here for this container, and what they did was they factored out the 3 pi because they have that in common. That's their common factor. And then over here, we have pi kind of already factored out of this volume, so they went ahead and factored the 3 out as well of the trinomial part, so that they got 3 pi as well, and they're left here with a trinomial, and they're left with x squared. Now we're going to factor the expressions to identify the radius of each cylinder. So here's our expression, x squared. So the radius of the first cylinder is x inches. Factor the expression x squared plus 10x plus 25 to find the radius of the second cylinder. So basically this first one here, x squared, they kind of factored that out anyways and they got x, right? So the factored version of that is just x. But to do the next one, x squared plus 10x plus 25, they're going to have to factor it. Now we notice that this is a perfect square and this is a perfect square. Okay, and because this is 2 times 5, and this is 5 squared, we know that this is a perfect square trinomial. So we're just going to have x plus 5 squared as our trinomial. So that's where they got this here, which means that the radius of the second cylinder is x plus 5 inches. Oops, x plus 5. So this is the radius of one of them. This is the radius of the other. The radius of the second cylinder, we're now going to subtract the 2 because the question is asking us to find the difference. And the difference is 5. So the larger cylinder has a radius that is 5 inches greater than the smaller one. This is just a way that we can use this information in these perfect squares to do it a little bit faster. It looks super complicated, but once you factor it out, it ended up being pretty simple. So what I want you to do is answer this question. What is the radius of a cylinder that has the height of 3 inches and a volume of, and it gives you the volume right there. So what is the radius of this cylinder using the information from the last one? Okay, we're still looking at perfect square trinomials, but we're going to look specifically now kind of going backwards at factoring the difference of squares using a pattern. So what is the factored form of x squared minus 9? Recall that a binomial in the form x squared minus a squared is called the difference of two squares, showing that a minus b times the quantity a plus b is the same as a squared minus a times b plus a times b minus b squared. So because these center pieces cancel out, you're just left with a squared minus b squared. What that means is when you are given a difference of squares, when you're given the first and last terms are squares and the middle symbol is a subtraction sign, in order to factor it, you're going to write the last term as a perfect square. 9 squared, the perfect square of 9 is 3 squared. And then you're going to write them as a binomial with one positive, one negative. So let's look at another example. Here we have the same thing, except that our first term is not just a coefficient of 1. Okay, so I'm going to do it over here before we see it written out. But basically, because I know this is a perfect square and this is a perfect square, I'm going to write 2x squared, that's my perfect square, minus 9 squared, that's 81. Okay, so my factored pair, my binomial is going to be 2x minus 9, 2x plus 9. Okay. Let's take a look and see if we did it right. Exactly, we write the first and last terms as perfect squares, and then one becomes positive and one becomes negative because these are difference of squares. So go ahead and factor your own difference of two squares. All right. What if I'm given a polynomial or binomial here that is a little bit more complicated? Okay, so when you have something that's a little bit more complicated, you can actually factor out a common factor first and then start looking to see if it is a perfect square trinomial or a perfect square, difference of perfect squares, things like that. So when you first see something like this, the first thing you want to do is factor out the greatest common factor of the terms if there is one. And that's the same in all the stuff we've been doing. The first thing you want to look for is simplifying. Is there a common term, right? So in this, we've got 3xy. So that's going to leave me with x squared minus 4y squared. So I just factored out my GCF from this polynomial. Now, taking a look at what's inside, I can tell that this is a perfect square and this is a perfect square. Okay, and because the center symbol is a subtraction sign, I know that it's a difference of squares pattern. So I'm going to have one be positive and one be negative. Don't forget that your GCF doesn't go anywhere. It needs to stay there. X squared is just x. Okay, one will be positive, one will be negative. And then 4 squared is 2y. That's the factored, right? These are my my perfect squares over here. So I'm going to have plus 2y, x minus 2y. And then this right here is my factored out complex little polynomial up here. So you're going to go ahead and try your own little complex polynomial. Remember to factor out those GCFs first and then look for perfect squares or differences of squares. All right, and we are done with our special cases here. So you can see that we went over factoring perfect square trinomials, both positives and negatives, as well as those with coefficients in the front. We're looking for a perfect square in the front, a perfect square in the back, and I can multiply by 2 times the a and the b or c terms. Okay. Then factoring a difference of 2 squares, we can tell that that's a difference when the first is a perfect square, the last is a perfect square, and the middle is not an addition sign. If it doesn't have those parentheses around it, then it's a difference of 2 squares. So we're going to have a positive and a negative binomial. It's when you have the parentheses around it that it becomes a perfect square trinomial. And so yeah, those are the 2 special situations that we learned how to factor out. Good luck and let me know if you have any questions.